This is a chapter on chemical thermodynamics, and when you look in your book, what you'll notice is that this chapter is actually broken down into two smaller chapters. The first chapter is called thermochemistry, which kind of exclusively focuses on heat and enthalpy. And heat is just an amount of energy going in different directions. Enthalpy is going to be a little more specific, which we'll talk about. And then there's also another chapter that deals with thermodynamics. And thermodynamics really focuses on the entropy, which has to do with chaos. And then also the spontaneity, which means like, will something happen? So those are the two kind of areas. One thing you really want to know or understand is that the entire unit is all about energy. So when we say energy, energy means that you have the capacity to do work. And if you take physics, it is a very strict definition that it's the force being applied over a distance. But typically in chemistry, we look at it a little bit differently. And we deal with energy, basically gains and losses during physical reactions or chemical reactions. So we typically calculate, okay, how much energy did we gain? How much energy did we lose? One thing you want to know is there's lots of different forms of energy. The two that we primarily concern ourselves with is kinetic energy, which we know is the energy of motion, and then potential energy, which is stored energy by where something is. So if you're higher up, you have more potential energy than if you're lower down. And then when we talk about energy, we're going to be dealing with the SI unit, which is the joule. And 1 joule is 1 kilogram meters squared per second squared. There's also the English unit, which you guys are all very familiar with, called the calorie. And when we say that you eat so many calories a day, calorie is energy, so you're eating so many energy units a day. So here's just a quick little simulation, if it likes us. Maybe not. Basically just showing you kinetic potential and potential energy and kinetic energy. So here is a pie chart. And what we're going to do is put the guy on here. And what's going to happen is you can see when he's at the top, he has a lot of potential energy. And when we let it go, you can see that there's a conversion between the types of energy. And you can see that there's a difference. And you can try different things. So if we restart now, here we have one where we have a ramp. And now this way we're going to start with a lot of potential. And then we're going to just convert to kinetic. And we don't regenerate it kind of thing. And we can change it. We can do a bar graph. So we can have him up here. And you can see that we have kinetic. We go to potential, or potential to kinetic. And one thing you want to notice is that the total amount of energy doesn't change. So that's an important thing to understand. Okay. Another really major thing in thermodynamics is that you're going to study a system. And what you have to understand is that a system can be the size of an atom. The system could be the size of the solar system. So you have to really be understanding, like, what are you defining as the system? What are you studying? And then everything else becomes the surroundings. And what you have to understand is you have to know what kind of system you have so that you know what variables you can control. And if you look on this slide, what they say is you can have 3 types of systems. You can have an open system, you can have a closed system, or you can have an isolated system. An open system is basically things can go in and out, matter can go in and out, energy can go in and out. Closed systems, you can let energy go in and out, but not matter. So this is typically what's studied because you kind of like control what's in it. But then what you typically do is kind of insulate it so that, that the energy inside is kind of constant. And then you can also have what's called an isolated system, where you don't let matter get in or out, and you don't let energy get in or out. An isolated system would be like a thermos if it was closed, because realistically there shouldn't be a lot of energy exchange. In a perfect thermos there would be none, and if it's closed there's no matter getting in or out. And then a big thing you have to realize is that whatever's happening to the one thing, the opposite is happening to the surroundings. So if the system gains, the surroundings loses. If the system loses, then the surroundings have to gain. And that's an important thing for you to kind of understand. You can't lose energy. You have to basically transfer it somewhere. So if someone gains, someone has to lose. And you just want to kind of understand, like, okay, what is the system and what type of system am I studying? All right, next one we have heat. And what we have is heat is represented by the lower letter Q, which means it's not a state function. So like the direction of the heat matters. And what we're going to do is heat is typically measured by temperature. And you want to realize that if you increase your Kelvin temperature, then they're going to have more kinetic energy and they're going to move faster. So if you look at this picture, we have a low temperature gas and you can see that they're not really moving that much. And then we have a high temperature gas and you can see that the arrows are much bigger and that they're going to be moving much more rapidly. We're going to watch you'll watch a short video clip on Bill Nye with heat in a little bit. And it's just a short clip just kind of talking about different things to think about with it. One thing you want to think about is like your amount matters. So if you have 500 mils of something at 25 degrees Celsius, has less energy than the same amount at 35 degrees Celsius. So typically, like if you have the same sample, the higher your temperature, then the more heat it's going to absorb. And you want to keep in mind that kinetic energy is related to velocity. All right, a couple other things about heat. When you're dealing with Kelvin temperatures, if you go to 0 Kelvin, that means that the average kinetic energy becomes 0. And basically that would mean down here that they would basically not be moving. So if you could reach absolute 0, then you would have no movement of particles. This is a Maxwell-Boltzmann distribution. You should have seen this before a couple times in AP Chem. And if you just remember that the lower temperature graph, you can see that on average the molecules are moving slower. And when you're at a higher temperature graph, that more of your more particles have more energy. And if they have more energy, they're going to be moving faster. So you want to realize that when you're a hotter temperature, your average kinetic energy is greater than the average kinetic energy of the cold system. Other things that you know about heat, but you should realize, is when you have things that are at different temperatures and they come in contact, there's always going to be a movement, and it always goes from hot to cold. And the energy will keep transferring until it becomes equal. And then basically you'll eventually reach what we call an equilibrium, where their temperatures are the same. And this is often like the labs we do where we have water and a metal and one's hot and one's cold, and then we let them go together until they reach basically an equilibrium. And that's what we're looking for. And there's actually a law about this. It's called the zeroth law of thermodynamics. And what it says is if that A and B are equilibrium, and B and C are in equilibrium, then A, B, and C are in equilibrium. One thing you want to realize is heat's not a substance. It doesn't have a mass. It is all about energy. And we're trying to get to what we call the thermal equilibrium when they're completely neutral. And then the last thing about heat, one way that you can calculate is this equation right here, Q equals MC delta T. Q represents heat, so you probably want to write that down. M represents mass, so if you have a larger mass or a smaller mass, that'll change the way things go. Delta T is your T final minus your T initial. And then the last thing that we haven't really talked about is specific heat, which is basically how much energy it takes to raise 1 gram of the substance by 1 degree Celsius. And it basically is like how much energy does it take to increase or decrease the temperature. Some things have low specific heat, like gold has a very low specific heat. Some things have a really high specific heat. Water has a very, very high specific heat of 4.18. So it kind of just depends on how the energy is distributed between the different molecules. And we'll use that in various calculations. Another thing you may hear about is heat capacity, which is a capital C, and that is for a specific object. That would be like 1 beaker. What is its heat capacity? And basically what you're saying is for that substance, that object, how much energy does it take it to move by 1 degree? But like if I do it for a beaker, it's only for that beaker. It's not for anything else. So you have to realize that it's very precise and it's unique. Specific heat is broader because you can apply it to anything that contains that element. And again, you don't use heat capacity very much unless you're working with really, really precise calorimetry.